So here we have our mass spectrum for diethyl ester. This is from NIST. They're a good government agency. They come up with all this stuff. So we got a large peak at 29, a large peak at 45, a large peak at 74. And here's your 31 right here. It's a branching peak off the 29. We also got this 146 out here. That's the full molecule. So just to let you know, these other tiny little peaks are kind of just anomalies. You don't have to really worry about them. This is 13 down here. That's a carbon anion. So don't really have to worry about those. So let's see. Here we have diethyl ester. And what you need to know about mass spectrometry, I like to use the acronym CAD. And that means converted, accelerated, deflected, and detected. So what this means is they're converted into ions by shooting electrons at them. So high energy electrons will split and fragment this molecule. They're accelerated down a kind of tube. They're deflected by a large magnet. So these positive ions are deflected by this magnet. They kind of have a trajectory, right? And then they end on this detector. So the heavy molecules go towards the top. They don't get deflected as much. So it's kind of like if you're trying to push a cement truck, is the example I've read. It's much harder to push, so that's why it will end up here. That's why we see the 146, the whole molecule. It's a lot heavier. Now the little tiny carbon anion, right, or whatever, that weighs 13, mass to charge ratio. That's like pushing a Honda Civic or maybe a bicycle. So it's way easier to deflect. So that's why we get our difference. So that would be that. So that's kind of a little refresher on the mass spec. So when it comes to fragmentation, I start looking at these carbonyl centers or anything that's kind of positively charged. So right here, you have this positive charge center and this positive charge center. Why is that? It's because dipole moment. So we have this dipole right here. So the electrons are going away from the carbon center based on a difference in electronegativity, right? So oxygen has like, what is it? Like 3.44 or whatever, and carbon is like 2.8 or something. Anyway, you're gonna have positive centers and negative centers. And so this is going to be very positive. And so if we get this electron getting shot at this molecule, what's going to happen is it's going to be attracted to that positive charge center and kick up a electron, and it's gonna fragment this molecule. So I'm gonna erase all this out of the way. Based on that, this molecule will fragment in a couple different ways. So you can kind of think of it as when this electron comes back down. So when this electron comes back down, it can go two ways. It could go to the left or it can go to the right. So option A and option B. So when it goes to the left, what we'll get left with is a couple things. So we'll have this guy plus this guy, right? Let's see. So that'd be option A. And option B, we'll have this guy. We'll have two of these guys, right? And so right there, and I don't know, it'll probably be like that. So here's our two ions. Now you can kind of tell, which one is more likely to form. So if we have two of these, you can kind of look at them and, intuitively kind of see that, well, these guys are probably going to be more stable. Why is that? Because this guy is really not stable. These two oxygens right here, or three oxygens, are all want their electrons. And as soon as that happens, another electron is going to come in and split this guy even more. So then you can start drawing the weight of these molecules. So this guy, right, this guy weighs 146. This guy, so we have the three carbons on the end, so that would be 15. We got 12 right here, and we got 16. So that's 10 10, 20, 30, 8, 40. So that's 10, 20, 30, 8, 38. So this guy's 43. Plus, we got 16, 12, 16, 12. Oh, 12 right there, 16, 16, 14, 15. I will need to add that up, but I believe that's the 74. So 16 plus 12 plus 12 plus 16. Oh, gosh. 16. So this guy would be 101. So we got 101 and 43. We can go to our Google and let me share this. Go back to our Google and we can see that that 101 and 43, those are pretty uncommon. So we can use our empirical evidence to show this. We kind of had that assumption anyway. So that would not be the right splitting pattern. It's technically, these are kind of like the anomalies. So yes, this happens, but it doesn't happen enough for us to really care about. So we can see that our splitting pattern would be these two molecules right here, kind of like a ester, acetylene, or some ion. So based on that, I know we have two of them. So that's kind of why we see peaks that are twice as much, because there's two of these guys. And we'll go ahead and put the weight right here. So we got 15, 14, 16, 12, 16. Go ahead and throw that in a calculator. 15, 14. And so this is how we get the 73 peak. Now this could change. Suppose, you know, a hydrogen sneaks in right there. That could be how we get the 74 peak. Who knows? Hydrogens like to kind of rearrange all the time. So that we saw that peak in our mass spec around 74. It wasn't very large, but it was significant. So that's where we got that guy. So now, based on this molecule, it can split in a couple different ways. We can really kind of look at the weight of how it splits. So if we split it, you know, right there, which seems pretty logical, we'll get a 15, 14, 16, right? And something like that, plus this guy right here, right? So 12 plus 16, so that would be the 28. That makes sense. So we got 15 plus 14 plus 16. So we got 45. And you got 28. And we did see those on our screen, so I'll share that. So we did see, we're seeing that 45 right there. Here's our 28 right in the middle. So it comes up a little bit. So that 45 is significant, so we probably would see those. So now back to here, this guy could split more. So out of this guy, we can get an acetylene. And actually, in this case, it's not an acetylene. It's kind of like a methylene guy. So let's see. Right. So we got our three hydrogens right there, and our three hydrogens right there. And this guy, so this would be 15 plus 14, and that's how we get our large 29 peak. So this is the most common anion that's going to be there. So this would be our 29 peak. And now suppose, and then what we'll have is an oxygen by itself. So we'd have like a 16 plus a 29. So that's one way this could split. So it could just split right there, leaving the two carbons and the one oxygen. Another way it could split is between the carbons. So you got a carbon, and let's see if I can basically homolytic cleavage, right? So an electron is going to go both ways and split that way. And what we'll get there is we'll get a carbon ion, so 15 or 14 or 13. Oops. So just a carbon by itself. And what we'll be left with there is a carbon attached to hydrogen, or a carbon attached to oxygen with 2 hydrogens there. So that's how we'll get the 30. Now let's say we may have some stray hydrogens running around here, and if you remember to organic chemistry, a secondary carbocation is not as stable as a tertiary carbocation. So a tertiary carbocation is much more stable. So if there's any stray hydrogens running around, or maybe it took it from this guy that left, so we do have free rotation. So as that splits, maybe this guy kind of latches onto one of those hydrogens. So that's how we would get the 31. So we do get 30. We also get 31, and we mainly get 29. So if we go back to our mass spec right here, we see a large peak at 29. That's the most abundant. So that would be those 2 carbons on the end. And then we do get 31 more often than 30. We do get 27 more often than 28. So this is just the hydrogens kind of moving around, but it kind of depends on what's split. So to summarize, we got our ion right there. It breaks down and we get this guy. This guy's about 74, this guy's going to break off into this guy plus this guy. That's how we get a 28 or a 28. Not as many of these guys. This guy could break further into just carbons and just oxygens. And then this guy right here can split 2 different ways. Maybe we'll get a carbon attached to carbon, and maybe we'll get a carbon attached to oxygen. So these are our main products. This guy could split off into carbons by itself, and etc. So depending on where the hydrogens go, makes the most stable molecules. So right here, this would be our 29 based on we had 15 and 14. So we had 3 hydrogens there and 2 hydrogens there. So that's how we get the 29, which is the most common, just the oxygen by itself. This way we'd have these 2 products, and we could get, most likely a carbon with 2 hydrogens on it. And this one would probably take the 3 hydrogens. And this is why the 31 peak is higher than the 30 peak. So this would be 31. So I hope that answered your question. That's pretty much the gist of mass spec. And hopefully you can explain it to your student.